Hello everyone and welcome to this SpaceAM webinar brought to you by Fluency Marketing. My name is Sarah Cruddas. I'm a global thought leader in the commercial space sector and I am your host for today. Now during this series of webinars, which will take us up to the live event in September at Leicester Racecourse, yes that is a live in-person event, we're here from materials experts, engineers and thought leaders as they talk about their latest innovations, case studies and market developments in the use of advanced materials in the space industry. Now today we're talking specifically about advanced materials and how on-demand manufacturing capabilities will make spaceflight safer as well as satisfying the strict requirements of the aerospace industry, all while remaining cost effective. Now, if you want to get involved in the live event or future webinars, please email info@fluency.marketing. The contact details are also in the chat box as a reminder to all of you. Now, just before we get started, and I welcome our speakers to the stage, you will receive a link to this recording and the whole discussion via email after the webinar, which you can watch back as often as you like, and also feel free to share with anyone who might find it of interest. Now, first of all, let's welcome our speakers. We've got Claire Baker, Segment Manager, Space and Communications at Toray Advanced Composites. Amool Raina, Program Manager, Oxford Space Systems, and Joe Summers, Managing Director at Airborne UK. Now, Joe and Amool, if you politely leave the stage, I'd like to welcome Claire Baker up to give her presentation.
Thank you, Sarah. Okay, I've crammed a great deal into what's supposed to be a 12-minute presentation, so bear with me while I go quite fast. What I will say is that Toray Advanced Composites materials fly on almost every space program in the Western world. We've been established in supply to space now for over 25 years. Our markets aren't exclusive to space, so we wouldn't class ourselves as a space company, but we also supply commercial aerospace, we supply high performance industrial. You can see some shoes, we're in sort of inserts for Nike shoes. There's a guy in the middle with a prosthetic leg, so we're in the medical area as well. And emerging areas like eVTOLs, where we're quite active at the moment, supplying all the programs emerging in that area. But space is definitely a core business for us and one we're very keen to continue to support as it grows dramatically. We have manufacturing sites in the United States and in the UK, which supply into the space sector. This is just a snapshot of our site in Langley Mill near Nottingham in the UK. This company was bought in 2013 and then expanded, almost doubled in size. And we basically moved a lot of technology, which we had in the US, over to the UK so that we could expand and grow into the European markets, which we were supplying by air freighting from the United States, but we needed a space in Europe to supply from. We've now got everything that we need to supply into the industry, and we're actively supplying space programs across Europe. On spacecraft, we're the structure, and we supply raw materials to manufacture these parts. So solar array panel substrates, reflectors, there's a huge list here of parts which we supply, but basically with composites, you can get about a third weight saving over metallic parts. And here are some examples of where we're used on launch vehicles, including a picture of me inside the Rocket Lab fairing. Their latest vehicle is substantially larger. I think they put a picture of themselves having dinner in it on their Twitter feed. So, and again, we're seeing growth in this area in small launch vehicles. And we're supplying to all the structural elements of these, including tanks for fuel like oxygen. So what are the challenges of getting to space? Well, it's very high cost per kilo. So as a rough sort of value, it costs you about $10,000 US to get to per kilo to get to geostationary orbit. On the small launch vehicles, they're still at a higher cost than the large launch vehicles, and they're going closer to the Earth. So to get to low Earth orbit costs you about $30,000 per kilogram. So you can see a weight saving is really worth it, even with quite exotic, expensive materials. The biggest load that these materials ever see is on launch. Huge acoustic and vibrational loads generated on launch. Excepting, of course, if they're going to go and land on other planets, that's a whole other set of loads. And then you get temperature shocks, for example, when you're filling the fuel tanks on Earth. Once you're on orbit, you've got vacuum, you've got radiation, and more we're seeing requests for materials that are resistant to atomic oxygen, which is basically oxygen escaping from the Earth's atmosphere. And of course, it's far more prevalent in low Earth orbit because you're closer to the Earth's atmosphere. So there are also temperature extremes in space as you're going in and out of the sun's shadow, and it depends how far away you're going from the sun with your mission. So there's thermal management, of course, no convection because there's no air to help you there. And you want long-term performance. So for a geostationary orbit satellite, you're looking at performance for 15 years in space without a failure. So you really want to know that you've got a good material up there. I'm pressing the wrong button here. So I'm going to whiz you through a few examples of where our materials are. This is leading nicely into Joe Summers' presentation because we are a supplier of the raw materials to Airborne, who make solar array panel substrates and who are now qualified to manufacture the substrates for European Space Agency missions. You can see a picture below that we both posted on our Twitter feeds, which is of the solar array panel substrates for the JUICE mission going to Jupiter's icy moons. So that's 85 square meters of solar array panel because it's quite a long way from the sun, so it's harder for it to generate power that far away. And it gets very cold out there. So it had to withstand temperature extremes, but also remain very stable as a structure, which is one of the advantages of composite materials, is you can get a very low coefficient of thermal expansion and coefficient of moisture expansion. So you're very confident about the dimensional stability of your product. You also need low outgassing. So what happens in space is that low molecular weight compounds literally boil off from materials, and those can then condense on things like solar array panels, solar arrays, and reduce the efficiency of electrical equipment. So we carefully control our materials to make sure we know how much outgassing will happen and that it's sufficient for the mission. This is an example of a product in the United States. It was developed in conjunction with Lockheed Martin, and it's the material which is used on the Orion heat shield. So it's very tough because it has to land back down in a splashdown into the ocean, as well as withstanding temperature extremes, so it mustn't crack. And it's a cyanide ester with a glass transition temperature of 348 degrees C, which is market leading in that area. Here is an innovative structure which has been developed by ATG Europe, one of our customers, and we've supplied the raw materials to manufacture these parts. And this sort of open grid type engineering structure saves a great deal of weight over a conventional solid or sandwich structure. So they're just getting moving in this area. Some of this work was funded by the European Space Agency, and they're now looking towards small launch and satellite structures with this type of application. And they are also supported by Airborne in the next stages of their program. And then you will have heard, if you're at all interested in space, about the constellations of satellites. What does that mean for us as an industry? Well, in the past, we've been slowly, carefully and methodically making larger composite parts. We now have to start to transition to making satellites not in 18 months or 2 years, but in a day or 2 days. And so that means that in the composites industry, we have to move towards automation of parts. And later on in this session, you'll hear from Joe Summers, who has some great videos showing what Airborne is doing in this area to allow sort of mass manufacturing of small solar array panel substrates for satellite constellations. And on smaller satellites, they still tend to be metallic in their framework. So potentially they will be composite in the future, but there's not enough weight saving there to move into that area yet. But this is probably a bit of a naughty slide, because I did grab this off Twitter and I can't remember exactly where, but there's a lot of movement in Europe towards supporting small launch vehicles. And this is the lineup of small launch vehicles and the larger launch, the Ariane, in Europe. And 3 of the German vehicles are in competition with each other, funded by Germany's government and the European Space Agency. There's a lot of composite structure on these, not just the fuel tanks, but also sort of the fairing and the body structures and struts and all of that. So this is all under development in Europe at the moment as we speak. Over on the far right, you can see Black Arrow's concept of a barge launch vehicle, which is something else that should be happening off for the coast of Wales, I think. And here you see, well, either you can get lots of small spacecraft up into space on small launch vehicles, or you can start packing them onto medium-sized launch vehicles. So our material was used on Vega's SSMS, which is the Small Spacecraft Mission Service. It's modular. At its maximum, you can get 50 spacecraft packed into the Vega fairing. And this is the most horrible slide, which I would be told off for, but it's my sort of thoughts about what's happening in space. And definitely we're seeing sort of larger launches, lower cost, smaller launches, more launches, reusable launches, greener fuels. There's been a push during the pandemic from ESA and the German government to sort of get moving here in Europe, which has actually accelerated all of the efforts, not just the German ones. The large geostationary orbit satellites, where we've seen the market drop a bit in the past few years, there's still demand for those, but there are fewer of them and they're more powerful. European Space Agency has done a great job through the pandemic in continuing to release funds and support things like the continuation of the Copernicus missions and supporting missions for that. We're seeing constellations of small satellites, more deployable and stowable structures. So Amool will be talking about those next, because that's an area where Oxford Space Systems specialises. Debris is becoming an issue. How will we clear it up? How will we monitor it? What sort of materials do we need to make sure that they're going to demise or burn up on re-entry? Flexible dispensers, drop-off vehicles, like we're seeing a lot of these launch vehicles with kicker stages, which then fly around, dropping things off into different orbital slots. Missions to the moon, Mars, other planets. We're even going to have a submarine going to a moon. That's sort of on the drawing board. Asteroid and meteor mining. All of these things, and HAPS vehicles is last on my list, which is the high altitude pseudo satellites, so things which are flying right at the edge of space, doing jobs a lot like satellites, but maybe a bit simpler to sort of launch them and land them again to Earth. So that's my time nearly up. You can get all our information on our website. We've got brochures that you can download. And we like to partner with our customers in order to deliver materials for these markets. So yeah, that's it from me. So I hope I've just about kept in my slot of 15 minutes. And I'll hand back over to Sarah. Thanks very much for your time and attention.
Thank you so much, Claire. That was such a fantastic presentation. I think when you were talking as well about the future space missions, looking at potentially sending a submarine to one of the icy moons of Jupiter, or Saturn, you feel like engineering and material scientists are basically magicians, because you're making science fiction reality. You're making all these innovations and enabling us to explore beyond Earth. Now, we've got a couple of questions in, but I just wanted to follow up with one or two quick questions before we cut across to audience questions. But in terms of, we're entering into a new space era. I think the events on Sunday with Virgin Galactic really cemented that, not just in the industry's mind, but in the general public's mind. But there's still one big hurdle, and you touched on this briefly in your presentation, and it's space debris. We've sent a lot of junk up into space and we haven't cleaned it up. Yes, we're improving the situation now, but there's a lot of existing junk. And I was just wondering, what role could material engineers, material scientists actually play in cleaning up space? Because we don't want to end up in a situation where we're actually prisoners of Earth because of debris we've left in Earth orbit.
Yeah, it's a massive issue. And fortunately, over the last few years, it really is getting attention now, and there are conferences on it. And it's not just the physical debris. There have been astronomers are very troubled by the interference, both of RF signal and also imagery. Trying to take photos of the night sky, they're getting these streaks from constellations of satellites as they're orbit raising mainly. But yes, there's a lot of debris up there. It's pretty much every rocket body that's ever been launched is floating around about 800 kilometers above the Earth. And our role as materials engineers, I think we can be involved in design of vehicles which can go and either make that debris more intelligent, so just attaching things to it that makes it know how to move out of the way of functioning satellites, or maybe pulling it back down to demise as it will burn up on re-entry. But the trouble being that not everything burns up completely on re-entry. So with composite materials, we're pretty confident that they do. But with metallics, it's not so clear. So yeah, it's a big issue. And one of the biggest issues is where's the commercial argument for doing this? So who's going to give anybody money to go and tidy up space? I think we have to somehow generate that from taxing, or just accept it as a responsibility of the space community. Who leads that? So it's not an easy question to answer, because there's no answer at the moment, but things are happening there.
You almost feel like there's always money in the unglamorous things, and taking out space trash has got the potential to be very lucrative if we can find an effective way to do it, just because if you get debris colliding with existing satellites, with astronauts in orbit, it presents a huge threat.
Yeah, exactly. So, I mean, I think large satellites move out the way of debris about once a week at the moment. So they just accept that then they're not operational, and then they have to put back in after it's moved out the way. So
that's an incredible fact. That's a worrying fact as well. I'm going to ask a couple of questions which come in from the audience, because we do appreciate we need to move on with time. So AJ has asked, great talk, Claire. So that's a statement, actually, not a question. Great talk, Claire. Sounds like autoclave prepreg is the material of choice in the sector. Any talk of using out of autoclave resin infusion type materials?
Absolutely. So maybe I didn't mention it strongly enough, but that Orion capsule is out of autoclave cured, because it's 5 meters across. So it was pretty tricky to be able to put that in autoclave. So as a composites engineer, the best thing you can do is put things in an autoclave. If you've got sufficient pressure, and then you've got pressurized air, you've got the most even distribution of temperature on your part. But absolutely, there are calls, especially on larger structures, to make out of autoclave parts, tanks, and fairings. I believe the Ariane fairing, now made by Ruag Space, is out of autoclave. So it is happening in the sector. I'm not quite sure what the fusion question was.
Any talk of using out of autoclave resin infusion type materials?
Oh, infusion. Sorry, I was thinking of fusion, like nuclear fusion.
Well, it's a different topic.
Infusion. Yes, there are. I mean, there are filament wound structures on space parts already. In fact, we've gone from a filament wound central structure for the Airbus satellites to a tape laid structure. So. And in fact, that's you get a higher fiber volume fraction, generally speaking, if you do that. So it depends on the structure, but these technologies are used in space. I would say that when I joined as a materials engineer to the space community, I was disappointed by how conservative and incredibly boring it was because people didn't want to take risks. And so you're not looking at a lot of new materials. You're very, very driven by, you only introduce a new material if it saves a massive amount of cost, or if the mission needs it. If you're going somewhere hotter or you're doing something that you've not done before, then you're forced to use a different material. But it is because the costs are so high to get things into space and operational, and then they have to remain operational for such a long time. You don't want to take risks with your materials. So we go around promoting space and saying how exciting it is, but we also need people to be very thorough, very meticulous, do every test, and we want to know that it works. We're pretty glad that we got Richard Branson up there and back down again at the weekend.
Yeah, and you forget the role of material science in a great. You kind of like the unsung heroes of space exploration.
Thank you.
Right, we're going to do two very quick questions. The next one is from Nilam. I apologise if I have not pronounced your name correct. Do the solar array panels have remote maintenance features?
No. That would be a very simple answer. No. Then they get less and less efficient as they're hit by micrometeorites, and they are sort of gradually degraded by the space atmosphere. And that is, towards the end of life of satellites, that is part of what dictates that they're going to stop working. So at the moment, no. And I'm not even sure if these space tugs that are being developed could replace them, for example. I know that at the moment people are trying to go to satellites and refuel them so they can sort of reposition themselves, basically. But whether they can then change or upgrade solar array panels, I don't know. Ask Joe that question. He might do it.
I'll save that one for Joe. Yeah. And just finally, this is from Stephen Beecher. Very informative presentation. Thank you, Claire. Has there been any interest in incorporation of sensors within composite structures, such as strain measurements, etc.?
I do know what you mean, and I absolutely, there's a place for it on the ground. In space, I think we rely far more on once it's up there, it's going to work, because if we know that something's failed, there's not a lot we can do about it, speaking very simply. So it's possibly of interest, and maybe it will be of interest when we're going to other planets, things like Mars sample return, and then we've got to lift off again from other planets. Maybe we do want to be checking out structures with a sort of embedded fiber optic cable, for example. But it's not been a big topic in space, but maybe we should think about it for that sort of thing.
Okay, wonderful. And that is, I'm going to pause there on questions. Thank you so much for your fantastic presentation, Claire. And if anyone's got any more questions for Claire, you can just put them in the chat box. And without further ado, if Claire, you can please virtually leave the stage, and if Amool, Raina from Oxford Space Systems can please virtually board the stage, enter the stage. I don't know how we say this virtually, but thank you very much, Claire. I will just wait for Amool to join. Hello, I was nervous for a second. So Amool, the stage is yours, and looking forward to your presentation.
Thank you very much. Thank you for having me. And thanks, Claire. That was a wonderful talk. So Claire's talked a lot about the material side of things, mainly from the carbon fiber aspect of materials. I'm kind of going to piggyback on that a little bit, as I am going to talk about fiber-based materials being used for space applications and the role that we've seen these materials undergo here at Oxford Space Systems. So to begin with, just a brief overview of OSS. As you know, we are and continue to strive to be the global leader in deployable antennas. And the reason why we could do this, why we are so good at what we do, is because we provide very simple, elegant solutions with reduced complexity, which are storage efficient, which are really low in mass, of course, owing to the really good and interesting exotic materials that we can use. And while doing all of that through clever design and engineering, we can reduce the overall price of the system that we are designing for. We have a range of products, and the reason why I throw this up is not really as a silly marketing trick, but it's actually to give you a little bit of insight, as we'll touch upon this towards the end of my presentation. The different antennas that you see which form the core product line of OSS, going from the Yagi antennas to the helicals, which are relatively small. They could fit in the palm of your hand size, to the larger antennas, the wrap ribs and the offsets, which could probably fit on a tabletop when they have been stowed. And if you open them up, they would, I would say, more or less occupy a small conference room. So the innovation that we have is not only in trying to have these products in a way that they are stowed in a very, very small space, but to also ensure that they are lightweight. And the only way we could do this is through the use of advanced fiber-based materials. And I'm going to touch upon a couple of them as we go through this presentation. We've got several materials that we use, going from carbon to glass to aramid, Kevlar, ultra-high molecular weight polyethylene, to metallic yarns and filaments. And I'm going to touch upon just the three critical ones that we have used or relied on quite thoroughly through our product development. And these are carbon, the ultra-high molecular weight polyethylene, and metallic yarns or the filaments. So let's start off with carbon fiber itself. And I know Claire's probably looking at this and saying, yeah, this is something that I could do much better than Amool. And she would be right to do so. I'm just going to give you a very brief insight from how we start off from a polymer all the way going to a finished product, because that gives you context into how these materials are developed and how we can use them and tune them to our requirements. So we start off with the polymer, a simple granular powder-based solution, which is then put through a spinning process. So you have a lot of additives, you have a lot of chemicals that go into it, something like dimethyl sulfoxide that is added to the base polymer. It's turned into a gooey sort of a liquid, which is then wet spun into fibers. And then those fibers are taken, stabilized through a heating process. So you increase the temperature, oxidize them in air, and then carbonize them as you put them through an inert atmosphere, raising the temperature even higher. Now, depending on the range of temperatures that you would use, you can either have, you can pretty much tune the kind of strength, so to speak, in very simple terms, of these fibers that you want. Depending on the sizing, the type of coating that you apply to these, you could either have pre-pregs or you could have dry fibers, and those then can be transformed into what we would typically refer as technical textiles. Now, the little box at the bottom is where the interesting things happen, because as engineers, we can't do much with the base fiber itself. So we do need to have properties that can withstand the different the harsh environmental conditions that you have up in space, but we have to take those fibers and turn them into something tangible, something usable that can be then turned in to products. So we start off with textiles, and I'm going to emphasize a little bit on a couple of processes which lead to different kinds of preforms that we use for our products. So a preform is nothing but a well-shaped piece of fabric or a well-shaped piece of a subcomponent, which is just one stage prior to its infiltration or impregnation with the resin, and then it goes through a curing and finishing cycle where it's made fit for purpose. So one of the elements that we use, or one of the types of materials that we have, of course, whether it's carbon fiber or glass fiber or any other form of fiber-based material, is a woven construction. So on the left, you see a weaving machine that is used to produce either a biaxial, a plain woven fabric, or a triaxial woven fabric. Now, depending on the kind of properties you need, you could either have these materials used for structural elements, or if you are clever enough and you know how to play around with the construction of the material, we have also successfully demonstrated the use of woven fabrics for primary reflector surfaces, something I'll touch upon towards the end of my presentation. Another form or another process that we could undertake is knitting. So imagine having your sweater or your jumper suit, which goes through a standard knitting process. Well, we use that very technology to create knitted elements or knitted preforms that can then be transformed into either structural or non-structural elements, which become critical key components of our products. So we do have an industrial facility here at Oxford Space Systems where we do produce knitted structures 4 primary reflectors, and I'll touch upon that in just a little bit. So an image that you see, we've got carbon fiber weft knitted structures that are energy absorption efficient. So you can have a woven structure which gives you a lot of strength, but if you want to have something that can withstand impact, then you would go for a knitted structure. And by virtue of the construction, the architecture of the knit itself, that gives you an additional benefit for absorption of energy. Another very, very critical and well-used form of preform is a braided structure. So the images that you see on the upper 2 images are those of a 3D braiding machine and a radial braiding machine. So we don't have these machines here, but we do work a lot with suppliers who can provide custom forms of tubular structures for us. So you could either have, a V-shaped integral structure that roots into a base structure, or you could have stiffening profiles where you have still got an integral structure, but you don't have to have a specific joining technique at the edges or at the point of confluence. In terms of plain fabrics, now not everywhere, not in every, as you heard Claire speak as well, you can't have every application where you could use a woven or a knitted or a braided structure. There are applications, there are structural requirements where you would want to have the maximum strength of the fabric or the maximum strength of the fiber being used. And for those, we use elements like non-crimp fabrics or UD tapes. So the process is, the image that you see in your background, this is a multi-layered Max 5 Liba machine that produces non-crimp fabric. So you could have multiple angles of unidirectional fabric laid on top of each other at a given angle requirement that you can prescribe, and we could use these quite smartly towards producing what we need for meeting our structural requirements. Finally, going on to the ultra-high molecular weight polyethylene, this is a very, very different type of material. It's a polymer-based material, much different from your traditional carbon fiber, but we have found its use quite interestingly in HDRM systems, so hold on and release mechanism. So you want to have, what we've combined is a material along with a production process that gives you just an excellent combination of the use of a filament, a use of a fiber, where you can restrain an antenna, hold it in place just up until it gets into space, and then through use of either a thermal knife or use of another means of severing this cord, you can cut this fiber and deploy the antenna, or cut this rope and deploy the antenna. The interesting thing about the ultra-high molecular weight polyethylene, such as Dyneema, for example, and there are several other, you've got Vectran and you've got a list of them, is that they have really good creep lifetime. So you can actually stow your antenna for a long period of time before you deploy it, and you can be sure that it's going to deploy just fine. The last bit in terms of materials is the use of metallic yarns. So again, we rely back on traditional textile processes, and we take these very, very fine yarns, very, very fine materials that are then knitted into either through a warp knitting process or a weft knitting process. Here at OSS, we work a lot with weft knitted structures, and these are used for producing the primary reflectors of our larger antennas. And we've also tested these, so we are in the process of going through an ESA qualification for these materials. So imagine something having a gold-plated yarn which is thinner than your hair. We sometimes have trouble viewing it when it runs in the machine, but those are some of the fun times that we have to deal with. So finally, coming to the applications, as I said, it's not just the materials exotic, it's also we apply them in a very ingenious way. So one of my colleagues, Dr. Yoshiro Oki, you can see him hold the ribs of the wrap rib antenna. So these are flexible structures that can be wound into a very, very small volume, and then they are deployed using a very good, so they basically rely on the strain energy of the material itself for it to deploy into space. The black fabric that you see on top is just just a representative fabric. That indeed is the metal mesh, which again is produced as a textile structure, but it is used as a primary reflector in our case. And then we've got the secondary deployment mast, which again is a cleverly produced carbon fiber-based structure where we can mix and match the way we layer up different unidirectional woven and braided structures in order to create a self-deploying structure. Very similar on the offset reflectors. I think the critical one that you see on the left-hand side in the image, this is roughly a 3-meter diameter reflector surface, which is made out of a carbon fiber reinforced silicon-based structure. So we've come up with a method of producing a flexible membrane that can be folded and unfolded, and it retains its shape once it's put in orbit. And this gives us excellent properties, and at the same time you can store it down into a very, very small volume. It's extremely lightweight and performance is just excellent. Apart from that, we use carbon fiber for the boom structure. Again, it gives you the advantage of lightweight. It gives you the advantage of collapsing it down into a very small volume and retaining it as we go forward. And last but not least, we've got our hinge rib antennas, where again we use a combination of either the metal mesh or the carbon fiber membrane. We can go up from C-band operation for something as low as 4 gigahertz of frequency operation all the way to up to 40 gigahertz. And these have been tried, tested, proven, and going through the final stages of qualification before we put them into space. So as I said, we have a lot that's currently being developed. We have a lot that smartly uses fiber-based materials, whether it's for the HDRM systems and the helical antennas, or the ribs for the wrapped rib antenna, or the main surface for the offset reflectors. The critical fact is that the choice of material and the choice of production process defines how we use these materials to our advantage. And finally, it's not just all show and tell. We do have a lot of heritage of putting these materials into space. We've had 6 major deployments. You're welcome to look up these names. The AstroTube was one of the quickest, longest retractable nanosat boom system that was placed into space. So we, I believe, hold the record even today of having the fastest time from concept to orbit, which is just under 18 months. And we created a system which was deployed. We have lots of helical antennas, one which was the latest one, which has been launched just a few weeks ago, and we are hoping for a successful deployment here in the next couple of days. So that's where we are. As I said, advanced materials do play a very critical role in what we do. It's not just from the lightweight perspective, but it's also from the lifetime, the operability, the storability, the cost. It makes it extremely efficient through clever engineering and production techniques. You can come up with systems, and we here at Oxford Space Systems have definitely developed systems that make use of these advanced materials to the fullest. So that's it from me. Sarah, back to you.
Thank you, Amool. That was a fantastic presentation. In fact, we've got one comment here from AJ, which says, wasn't expecting a composite textiles masterclass from Oxford Space Systems. Nice. So thank you so much there. We've got a couple of questions, and then if you have got a question for Amool, of course, please put it in the question section of the chat box, and if Amool can't answer them now, he'll try and answer them after we finished on stage. So just one quick question that I wanted to follow up with you, and it's kind of an open-ended question, so do forgive me. Now, how much potential have we got in terms of disrupting the space industry with the smart use of fiber-based materials? I mean, how much disruption? We're seeing an extension of life on Earth beyond, life beyond Earth. We're extending humanity's presence in Earth, but how much potential has this got to disrupt the way we can access space, the way we can utilize space to not only benefit Earth, but extend humanity's presence into space?
There are two factors to it. The first factor is if you look at the small antennas, we are trying to solve problems that are occurring by the day here on planet Earth. And the only way to get ahead of ourselves is if we can produce a network of satellites, a constellation of satellites that can give us real-time data, and they can be put into space in a very short period of time. So with the use of the helicals or the Yagi antennas, as Claire mentioned, we have gone past the stage where it would take you 18 months to 2 years, 3 years, or 5 years to produce an antenna and put it into space. Now, using advanced materials, using advanced production techniques, we can go from a blank sheet of paper to a satellite or an antenna in orbit within a matter of a couple of months.
Wow.
And to answer the second aspect of it, which is looking at the humanity side of things, obviously Earth is growing smaller and smaller by the day, and we are exploring the use of other planets, the potential use of other planets, or potential use of other planetary bodies to extend the human life. For those as well, we rely quite heavily on advanced materials because we have to have larger, higher precision, higher quality, longer lifetime antennas or satellites that can make that journey to that particular planet to map out what the resources there are. Is it inhabitable? Can we have something? Do we understand the geology, the geography, the overall atmospheric conditions of this particular place? So it's not just about, as I said, using advanced materials for lightweighting, but it's also to making antennas, making satellites that can withstand the journey to another planet, that can sustain their life cycle without being destroyed, and provide us that critical information that will form the basis for perhaps the next few generations of mankind.
And what does it mean to you on a personal level? Because you're so enthusiastic, but to be doing this, which can have such an impact in humanity, exploring beyond Earth.
It is quite exhilarating. It is each day when we come here to work, it's not just me, but the entire team here at Oxford Space Systems. We always believe that we are contributing towards the benefit, the advancement of mankind. So it's not just about a commercial entity, but we have a larger vision, a larger goal in mind, where we are trying to solve problems for people, for humanity, for humans here on planet Earth, while at the same time having a broader vision of, okay, maybe 100 years from now, there would be a human settlement on Mars or on the moon. And we have to think about solutions as to how we can have those answers of what the conditions on those planetary bodies are well before we make that trip.
And we've got a fun question which Claire has put in, and she says, what's the smallest packing to largest deployment you can do? E.g., can you pack a 10 meter diameter reflector into a matchbox? Now there's your challenge.
There's a challenge indeed. Well, we haven't gotten to the matchbox yet. I could tell you that we are getting close, especially with the Raptor antennas. We can pack in a 3 meter or 5 meter diameter into under a meter of volumetric space. So this is taking something, as I said, as big as when deployed, it would probably fit into a conference room, but when you compress it down and fold it down and stow it, it can fit just on the desktop of your table. So we will probably get to the matchbox level, hopefully sooner rather than later. But yeah, we are on our way to that point.
That's fantastic. I feel like that's a challenge now set for you. We've run out of time, unfortunately, but there are a couple of more questions in the chat box. If you'd be so kind as to answer them, that'd be wonderful. And do please keep your questions coming in, because we can get them answered after the presentations. And thank you very much, Amool, Raina. It was a fantastic presentation.
Thank you very much. Thank you for having me.
No worries. And if I can welcome up now, last but not least, Joe Summer, who's from Airborne UK, with his presentation. Joe, welcome to the virtual stage with your great virtual background as well.
Thank you, Sarah. Very kind of you in both respects. Yeah, and thanks to Claire and Amool. I'm not sure how I followed that. The level of detail, informative presentations, and the enthusiasm level. So I will try.
We've all gained a PhD. If we didn't have a PhD this lunchtime, we've all gained one now after that.
Absolutely. Okay, let's try and not take any energy out of the call, and I'll move on to the Airborne presentation. So yeah, thanks for the invitation to Fluency. Just to introduce myself briefly, so yeah, I am Managing Director of Airborne UK. I'm also Commercial Director of the automation business. I mention that because what I'm not is involved in the Airborne aerospace space business directly. So I'm presenting to you a lot of content that would come from my colleagues in the actual space business. By which I mean, please be gentle with me in your questions, or at least if I answer them poorly, you'll understand why. So I'm going to quickly introduce Airborne as a company. I'm going to show you what manufacturing techniques we've developed and how we go about improving the cost-effective, high-rate production of space components. We've heard about clever structures. We've heard about interesting materials. And thanks to Claire for referring to Airborne a couple of times in her presentation. I probably could have paused at that point. Our sales efforts were done there. But yeah, what we're focused on is trying to improve the efficiencies and conversions of composite materials into usable structures. So I'll try not to make this too much of a corporate overview, but just so everybody who doesn't know Airborne, we're about 130 people, facilities in the Netherlands and in the UK. I run the UK, but the Netherlands the larger part, and that includes both the automation business and the aerospace business, including our space production business. We come from a background of making composite structures. We understand that extremely well. I'll give you some examples shortly, but our vision is towards automation and eventually digitalization of composite structures. So I like to remember myself that automation is in fact Industry 3.0, and the world is talking about Industry 4.0. So even the application of automation to composites is by no means complete. But our vision is towards how you digitalize that, and that's adaptable factories, that's being able to collect data and optimize your factory on the fly, working with automation systems in how that's achieved. A variety of examples, just mainly to describe the heritage of Airborne. You have some examples of some space components on the slide, but there has been a business spun off now with a different name called Airborne Oil and Gas. We developed a lot of automation capability and high quality, high rate production through being able to produce thermoplastic spoolable pipes. However, today we focus more on structures in the space business, aerospace business, and expertise around marine. You'll see some examples of tidal turbine blades, FRP propellers. You'll see some land-based antenna structures, solar array panels, and structures for civil aerospace. These things are all markets which have taught us how to automate and the value of composite materials in different segments. This is what sets us apart. It's true of the composites business, the automation business, and us in the UK. We combine composites know-how. I think it's pretty difficult to get away from having to needing an expertise in composites. But we combine that with the mechatronics side, so that's the automation side, and then the software engineering. I have a couple of videos which I'm going to show you at the end. They really describe better than I can what our vision is for a smart automated factory for producing anything, in this context, space components. And our philosophy there really is the application of these three themes in order to achieve that cost-effective solution for composites. Here are a couple of the automation cells that we apply and use in order to produce composite structures. Composites are, unfortunately, today quite a wasteful process in many contexts. The buy-to-fly ratio, if you call it that, is not particularly good. A lot of materials end up on the cutting floor as waste or lack of useful materials. And our goal is to not only automate in the sense of improving productivity, reducing labor, but to minimize the production waste. So you have a variety of manufacturing cells here that are either automatically dispensing resin. So typically 40% of resin in a potting process is never gets to the part. In this case, that's considerably lower. Our systems for automated kitting often save 10 to 20% of materials from gross usage. So yes, there's economic benefits. There's also sustainability benefits. And finally, we hope in the end, the composite structures we've produced are more cost effective as a result. To eventually make our way back onto space, which is, I know what people are here to listen to. These are the products that Airborne is working on. So we are the market leader for substrate panels. We've seen a few examples of that already from Claire, where we produce these panels extremely high stiffness for mounting solar panels too, and some very interesting missions that we've been involved with in that respect. Also structure panels for satellite structures, and a variety of programs in the small launcher space, where again, new paradigms, new requirements for cost-effective and higher rate structures are needed, and we're internally applying our own automation capability to make that viable. Just a quick word, we do help clients quite considerably in not just supplying components or necessarily supplying a machine, but as very well described by Amool and Claire, in fact, designing a composite structure is a series of trade-offs between the economic requirements, the functional requirements, the chosen manufacturing technology, and that's a journey which is not that easy to navigate. So Airborne also does support clients in helping choose the right materials for their structures, in choosing the right automation solutions, in thinking about the right compromises in designing new composite structures. So if I can, hopefully someone will present the video, which will do a much better explanation than me of Airborne's.
New space is starting a movement of change. The commercialization of space requires drastic cost reduction in spacecraft manufacturing, an unprecedented production volume. Airborne believes that design to cost and process automation are key to meet market demands. Sandwich panel manufacturing is our core business. This enables us to redefine the process and to cut down to a fraction of the cost. We do this by applying disruptive technologies for panel laydown, curing, machining, and inspection with integrated logistics, and by panel manufacturing on highly automated production lines, assuring a robust process with stable quality and high throughput. Mega constellations will catalyze the accessibility of space. Airborne is committed to be your partner in enabling the business case for affordable satellite constellations. Connect the world. Connect to Airborne.
There we go. So I should have just played that at the beginning and kept quiet myself, shouldn't I? There's the vision, and we've got a second video which we're just going to show you. It's Airborne in 90 seconds. And so while you've seen the sort of CGI vision, we now have some more real practical examples of how we're deploying this technology into the real space structures. If we could go for the second video. There we are. So if you're a fan of composites and driving Euro pop music, then that will be the video for you. So that brings me to the end of the presentation. I hope I've given you a flavour of what we do at Airborne. And back to you, Sarah.
Thank you so much, Joe. You did not disappoint in being the icing on the cake of this stellar lineup that we've had for today. So thank you so much for that fascinating presentation. We've got a couple of questions come in, and a reminder, if questions can't be answered, we'll try and get them answered after the presentation. One thing I wanted to pick up on, Joe, and it was at the start of your presentation, you were talking about smart automated factories, and we know that one of the big things in the commercial space sector, certainly Jeff Bezos and Blue Origin, they're looking at taking manufacturing away from Earth, doing manufacturing in space in order to look after Earth. Now, forgive me, because you've already given the caveat that space isn't your expertise, it's more the general stuff, but what potential has Airborne got to actually help with making off-planetary manufacturing a reality and having automated factories off Earth to benefit both the space ecosystem as well as life on Earth?
Yeah, that's a good question.
Sorry.
I mean, the principle, let's say, of a dark factory is something that's very much in our roadmap. So the idea that somehow you can, lights off without any human intervention, have an adaptable, fully automated digital factory. And we've gone quite a long way towards having the ability to achieve that. So, for example, we have a web browser portal whereby you could design a laminate virtually, and then the robot code is generated remotely, and the robot will produce the laminate that you've designed through the web browser. So in theory, you could extrapolate that outside the Earth's boundaries. Quite how practical it is to fly these quite heavy robots and things out of our atmosphere and have them economically deployed elsewhere, I guess that's a little way off. But at least, the challenge is there, and it's something that we're working on to achieve here. Maybe in future we can get it done somewhere else.
I think the goal as well would be to manufacture the robots in space, so to take all the heavy lifting. You've got companies such as Made in Space in the US and other manufacturing ones to actually create things in space so that we don't have the costs associated with launch. Yeah,
and that's right. I mean, and Airborne, we don't profess to be, we don't design robots, we don't make robots. We're trying to integrate the technology and really focus on the digital means by which you can program those robots in an automated way and have the intelligence of the robots. And I think those are the fundamental things that are needed. And hopefully someone else can solve that problem of how to build the robot with a robot somewhere else.
But the potential certainly there, and I think that's absolutely incredible. We had a comment come in from Peter Slinger, and he says, and Joe, you might actually want to go into questions box to answer this. He says, "Hi Joe, very informative presentation and well delivered. We've had great presentations today. Would Airborne be looking for a technical partner and supplier to help get to the digital on-demand stage in terms of composite productions?" And he's left his details in there.
Yeah, absolutely. Happy to talk to Pete about that. Automation equipment needs to be used by someone. I think the kind of very fashionable term is production as a service. At the moment, we think about quite different business models for our equipment and how it gets deployed. People might think about rental, about subscription models. I mentioned dark factories, but essentially once the production line is fully automated, it's then a question of who hosts that. That could be us, it could be a variety of other people. So very happy to talk to people who might have some interests.
Okay, thank you. Joe, that is, I'm going to stop there because we are bang on time, which is absolutely fantastic. Joe, that was an incredible presentation. If anyone's got any more questions for Joe, you can reach out in the question box now or reach out afterwards as well. And I wanted to thank all our speakers. So we've had Amool, Raina even, and also Claire Baker. So thank you so much for your time today. And there is one question which has come in from Joel Strickland for Amool, and if we can get connected so that question can get answered, that would be fantastic. Now, so this brings to today's webinar to an end. Many thanks to our speakers and of course Fluency Marketing. Remember, if you didn't get a chance to get your questions answered today, we'll do our very best to ensure that you can get an answer via email. The next webinar, the final webinar in this series, will be held on the 10th of August. Now you can register shortly via advancedmaterials.events. That's advancedmaterials.events, where you'll also find more information about Fluency Marketing's Marketing's Advanced Materials Conferences. Now, if you'd like to watch today's presentation back or share this webinar with anyone, you're very welcome to do so. You'll receive a link to the recording of the discussion via email in the coming days. And once again, thank you so much to all of our speakers. It's been an absolutely fantastic event.
Thank you.